So, in chapter 7, which I'll start today. I guess we can just go back and do chapter 6 again, right? It's just like repeat. It's okay. In chapter 7, 7:1, 7:2, 7:3, 7:4, 7:5. We're going to do, today we're going to start these two, which are inverse trig functions. I don't know how much you remember about inverse functions, okay, but if you remember nothing, you're going to have to review a little. But we're going to do inverse trig functions. Then we do solving trig equations. And then identities, proving identities. So this is kind of like those questions you've had on your quizzes recently that say, use identities to simplify this. Okay, except more intense. And then we do angle sum and difference formulas. And then half angle and double angle. So it's really more it's really more at this point saying, how can I figure out all the possible relationships that there are between these 6 trig functions? So we're going to go in depth and study what kind of relationships we have. The inverse trig functions and solving equations are a little different, but this is studying all the relationships between the 6 trig functions. Well, let's start. Let's start with inverse functions.
Josh, I had a question about the tangent graph.
Oh.
So it would be wrong. It's fine. It would be wrong to only graph just one segment of it. You have to actually graph 2 to get the whole period, right?
Right. So this is kind of what Brian asked. You can do it with one period. It's just the cotangent graph that will result is very ugly. Like just original tangent. Right, the regular tangent graph, if you only graph one period, he looks like this. And if you try to change that into cotangent, this guy will be your asymptote right in the middle.
You
and
really
then
don't
these
have
guys
to
will be
redraw.
zeros.
You really don't have to redraw it. It's okay. I think you've already answered my question.
Right? So what happens is this guy ends up looking super funny, right? He looks like this.
So it's only half.
So, but it's the whole graph. It's just not the way, right? Because there's half of it here and half of it here. It's just we've kind of split the period in a stupid place, right? So what we would really like is to have a second asymptote so that we can see the overall trend here.
I see.
That's why we went out further on.
So we split the normal period in half.
Yeah, it kind of splits what you want your period to be, which is between 2 asymptotes, and it puts an asymptote right in the middle instead. Like I said, it's more for prettiness than technical correctness. Technically, this would be a cotangent graph, but it's just not. And I've gotten that answer on tests before, and I've given credit because it is cotangent. All right, so what do you guys know? So I'll talk about inverse functions for 20 minutes. Confusing. Hopefully clear it up next time. What do you guys know about inverse functions? Any idea what an inverse function is? A reflection across the y equals x line is one definition. What else? What do inverse functions do? Not reciprocals. Not reciprocals. All right, if you remember, sort of a 126 review maybe. If I give you a graph, here's a graph of some random function here. Say it goes through, I don't know, -2, 0, 0, 1, shoots up to 2, 6. which is your original function, like this. Yeah, so if this is f, what happens on the inverse function? X and y switch. Okay, so the inverse function, one way of thinking of it is that x and y switch. So instead of having negative 2, 0, you're going to have 0, negative 2. Right, on the inverse function, this guy switches down here. See, these guys just got flipped. And instead of having 0, 1, you're going to have 1, 0. And instead of having 2, 6, you're going to have 4, 5, 6, 2. Right, 6, 2. The idea is that an inverse function gets you back where you started. So for example, if you're on the regular function f, f takes the x value of negative 2 to the y value of 0. But if you think about this as a relationship, it matches negative 2 up with 0. But then on f inverse, you go backwards. 0 gets you back to where you started, negative 2. Right? Negative 2 goes to 0, 0 goes back to negative 2. Right? So inverse functions undo each other. Another consequence of this switching x and y is that domain and range switch. Right, if you look at, for example, the domain of the green graph, the domain of f was what in this picture?
Negative 2 to 2.
Yeah, smallest x value, negative 2. Largest x value, positive 2. So the domain was negative 2 to 2. What's the range of the purple graph, the range of f inverse?
Negative 2 to 2.
Yeah, so if you look at the purple graph and focus on range, the y values, the lowest y value is negative 2, and the highest y value is positive. So domain and range switch between the original function and the inverse function. I have one other comment to make before I go back to trig. There is a condition that we need, and this is really what makes our life super hard in trig. There's a condition that we need for an inverse function to even talk about an inverse function. Right? So not all functions have inverse functions. For example, if I draw you x squared, which looks like this, if I try to switch all the x and y values here, so just take some sample points here, say negative 3, 9, right? Because if I square negative 3, I get 9. 3, 9, and 0, 0. What happens if I switch x and y? What points do I get? So 0, 0 is going to stay, right? 0, 0, if you flip it, you get 0, 0. But if you do negative 3, 9, and you flip it, you get 9, negative 3, which will be way over here. And if you do 3, 9, and you flip it, you'll get 9, 3, which will be which isn't a function. Right? That's the problem. This guy fails. This possible inverse function fails the vertical line test. So what condition do you need on the original function to make sure that this inverse is a function?
Can't be squared.
Oh, okay, but that's a little too specific. That's true, but too specific. So if I draw, what does this vertical line correspond to back here on the original? A horizontal. So if your original function fails the horizontal line test, then your inverse function will fail the vertical line test. So in order for a function to have an inverse function, it has to pass the horizontal line test. Which is really, really bad for us, because if you think about any of our trig functions, sine, cosine, they all repeat. And they fail the horizontal line test miserably. So this is going to cause us some problems. But we'll fix it. We'll fix it. It's okay. It's all right, guys. I know. I know, you're very sad. Okay. No, it is broken. That's what I was just telling you. All right. So let me talk about the inverse sine function. The problem, so let me draw, so this is about the inverse sine. So let me start by drawing the regular sine function. So the regular sine function, let's see, quarter periods are pi over 2. Let me go back a little bit just to be cool. I don't know. So sine bounces between -1 and 1, but it starts at a 0 at the origin. Right? So it goes 0 max, 0 min, 0. One period of y equals sine x. Let me go ahead and go back a little bit too. I'll show you why in a second. If I went backward, it would go min 0 and then max 0. As you can see, horizontal line, even on what I've drawn, I hit a horizontal line 4 times. And I haven't even drawn it all. That keeps going. So what we do to fix that up is we do something called restricting the domain. So I'm going to change the domain of my sine graph for this application. Instead of assuming that the domain of sine is all real numbers, which is what we usually assume, I'm going to restrict it to a smaller window. And usually the window we restrict to is negative pi over 2 to pi over 2. So on this window right here, where I only have this portion of my graph, this portion of my graph does pass the horizontal line. So we're going to consider the restricted sine function, which is the same as the regular sine function, but it keeps the x values, it only allows x values between pi over 2 on the right and negative pi over 2 on the left. This is called a restricted domain. So basically, we're just going to ignore all this other garbage for our application. Pretend it's not there. Only focus on this. So then, restricted to just this domain, I can define what the inverse sine function does. So the notation, well, there's a couple of notations, but the one we're going to use for inverse sine is going to be sine to the -1. So saying y equals sine to the -1 of x, this is read y equals sine inverse of x. This is equivalent This is the inverse of the sine function, so this is going to be the exact same thing if you went back to the original sine function, but switched the roles of x and y. This is probably meaningless to most of you, because there's kind of too many symbols for this to be accessible at the moment. But basically what you should take from this is to do anything with inverse sine, you're going to rewrite it as original sine. Okay. Now, to help you sort of understand what all of these symbols mean, I want you to think about back in the original sine function. So over here, what does y represent and what does x represent? And why? Like what do you feed into sine? What does sine always take in? An angle or a ratio?
Angle.
Angle, right? Sine eats angles. You always do sine of pi over 2 pi over 4, sine of some angle. So this guy, the thing that's being fed into the sine is an angle. No matter what I write here, whether I call it y or x or theta or cubert, okay, it doesn't matter. If it's sine of something, that something's an angle. And then what gets spit out here is a ratio. That's how sine works. So what inverse sine does is it goes backward. Inverse sine eats a ratio. So the ratio is here now. And it spits out an angle. So inverse sine is going to spit out the angle that makes sine equal to your ratio. The one sort of catch, the one thing that's going to make your life very difficult is that the angles over here have to be between negative pi over 2 and pi over 2. Right? That was our restriction. We had to restrict sine so that the angles we put in were between negative pi over 2 and pi over 2. So this angle that you get out over here must be between negative pi over 2 and pi over 2, including. So I put this in the remark up there. It says the input of sine inverse must be on the interval negative 1 to 1, and the output must be between negative pi over 2 and pi over 2. So what I'm saying is, I'm repeating what I said, that this angle has to be between negative pi over 2 and pi over 2. But I also want you to realize that this ratio that you put in has to be between what and what? Negative 1 to 1. This guy, the thing that you put into sine inverse must be between negative 1 and 1. Why is that? Right, that's the range over here. Right, the ratios you get out of sine are always between negative 1 and 1. So the ratios you put into sine inverse must be between negative 1 and 1. If you put anything outside of that, sine inverse is going to die. If you try to do anything that's outside of negative 1 to 1 for a ratio, sine inverse won't know what to do and it'll explode. So let me do a couple of. So you got to be careful with sine inverse. It's a dangerous situation. All right, so it says find the exact value of each expression. Sine inverse of positive 1/2. Yeah, so to understand what this means, you got to break it down, and I have to break it down in terms of ratios and angles. This is saying I have a ratio of 1/2. And sine inverse is going to give me the angle that makes original sine equal to 1/2. So to rewrite this in terms of original sine, you would say sine of theta, sine of some angle, has to equal 1/2. And then you would go in and solve for this theta. In order to solve for this theta, you kind of have to have a good idea of what your unit circle looks like. Right? Because at this point, you have to have some picture of all the possible sine values we know. And so you come in and say, oh, I remember something, nothing else. And I know on the unit circle, the sine value of 1/2 occurs right here at pi over 6. So this, Right? I focus on the y-coordinate of the unit circle because I'm dealing with sine inverse. And so this is asking what angle makes sine, what makes your y value equal to 1/2. So the answer to this, you would write sine inverse of 1/2 equal to pi over 6. It's equivalent to solving this equation. Okay, so that's okay, that's fine, right? That's fine. Now here's what's not fine. There is another place on the unit circle where sine is equal to 1/2, right? If I keep going and I draw my second quadrant here, if I reflect, this guy is going to be equal to 1/2 again. Right? The x will be negative, but the y will still be 1/2. So how come when I'm doing my sine inverse, I didn't focus on this 1/2, and I chose to focus on this 1/2? How do you tell the difference?
Because you restricted yourself?
Because you've restricted yourself. Now, more specifically, this angle is 5 pi over 6. And I know all of my angles have to be between negative pi over 2 and pi over 2. So on the unit circle, here's negative pi over 2. Here's pi over 2. When you do sine inverse, your answers always have to come between these two rays. This guy is outside of my possible range for sine inverse, so I don't even consider him. This is the only place where I have a y value of 1/2 in this area. So, one more and I'll let you go. What about sine inverse of root 2 over 2? So this is asking the question, when is original sine equal to root 2 over 2? So you look here at the y value of root 2 over 2, and you go back to the angle, which is pi over 4. So sine inverse is going to get you back from a ratio to an angle. So the answer to this would be always in radians, never give me